Let's get this morning's program started. So the first speaker is Lothar Goettsche from Abdus Salam ICTP, and he'll talk about Verlinde formulas for service.
Okay. Thank you very much for the introduction, and I'm very thankful for the invitation and also for having spent a month now and the month in March at this program, which was very nice and interesting, and for all the nice talks before, and maybe all the nice talks after this one, which will not be so nice. But okay, so I wanted to talk about some kind of version of within the formula for surfaces, but I should say I'm talking about the conjecture. I'm not going to prove a theorem. So no, it's so it's supposed to be. So let me introduce what I'm talking about. So SH is a polarized projective surface. Say over the complex numbers, we assume that the geometric units of the surface is positive, and say the first Betti number of S is equal to 0. If you want that it's simply connected or whatever. So we look at this moduli space, which is just moduli space of rank R stable sheaves with Chern classes C1 and C2. So rank R semi-stable sheaves with the corresponding on S with respect to H. So here, this C is an element in the Grothendieck group of vector bundles on S. I know, just it's the class of an element in the modular space. I just want to abbreviate it with the C because I find it useful to use this. So C class of E in the modular space.
Do you have some smooth?
What? Well, yeah, no, certainly. I hope I said it, but I certainly didn't write it. Okay. So now this moduli space will normally be very singular. But it has an obstruction theory, so as a perfect obstruction theory, at least a stable is equal to semi-stable of a certain dimension, which we will anyway need, of expected dimension ED of C, which is 2R C2 minus R minus 1 C1 squared minus R squared minus 1 the holomorphicEuler state of S versus standard. Okay, so this is the space, and so if one has this perfect obstruction theory, it gives you two things. It gives you the virtual fundamental class, which is in, say, the Chao group corresponding to the virtual dimension of MC, and it gives you also a virtual structure sheaf. In the Grothendieck group of sheaves on MC. Okay, we want to use this structure. So I want to give this kind of Verlinde formula. So I'm not, I don't know about conformal blocks or anything. So for me, a Verlinde formula is just a formula for the dimension of spaces of sections of determinant bundles on this moduli space. So Verlinde formula. So what do I mean by this? So we have first the determinant bundles. So I write KC. So C was our class here in the Grothendieck group. KC is equal to the elements in the Grothendieck group of S, which are sometimes orthogonal to C, namely the holomorphic Euler characteristic on S of C tensor B is equal to 0. And as we had also seen in earlier talks, I think on Tuesday, in such a situation one can define a corresponding determinant line bundle. So if we have here MC with a projection, so if we look at this product, then we can, and we assume for the moment that we have a universal sheaf. Then there is a formula for this. Then we can find the determinant line bundle by standard construction, namely we can call lambda of V to be the determinant of E over shriek, so the push forward of the pullback of this V, tensorized with the universal sheaf, and then we take actually the dual, and this will be a line bundle on MC. And so we don't actually need the universal sheaf, so the way it's defined, because of this condition here, it's independent of what universal sheaf we take, and it's so independent of it that we don't actually need to have a universal sheaf. No, it's just enough to have whatever, to descend it from the what's needed, whatever. Okay. So now we can define the Verlinde numbers. Yes.
So here, at some point, I was assuming that all semistable.
So yeah. So if you want, you can assume that it's a reasonable assumption. Otherwise, what I say is not quite literally true. But as I anyway make a conjecture, I claim that this conjecture will be true also when stable is not equal to semi-stable, and then one has to use change definitions a little bit and use something like choice song pairs to define what I'm talking about. But it might be reasonable to assume that stable is equal to semi-stable, then there's no problem with that. But if you make, but anyway, I'm sure the conjecture also holds with the correct definitions in general. So my Verlinde number will be just, I take the holomorphic Euler, so the so-called virtual holomorphic Euler characteristic of MC, which is line bundle lambda B, which is defined to be the holomorphic Euler characteristic of MC and lambda tensor virtual structure sheet. And now one would expect that if C2 is very big and say the first Chern class of V is also very positive, then this thing should be equal to just this virtual holomorphic Euler characteristic should be just equal to the dimension of the space of sections. But we don't really care about, because the random moduli space will be generically smooth of the expected dimension, and one expects no higher homology, but it doesn't matter. We compute this virtual holomorphic Euler characteristic, which is always one. So a Verlinde formula will be the formula, so a generating function, formula for these numbers. And in form of a generating function. So this would be an analog for the Verlinde formula for curves, where one has computes precisely the same thing. Okay. So I should briefly, let me see, I could briefly also mention another related problem, which I then we're not talking about. We can also talk about the so-called Segre formula. So in this case, we can, for V, element in the K group of S, we can define element. So or something, an element in the K group of tensor Q of the moduli space. We take the minus E lower 3 Q upper star of V tensor the universal sheaf times the determinant of the universal sheaf to the 1 over R, the minus 1 over R. So if this thing doesn't exist, we can certainly use a Grothendieck to define its Chern classes, and we only work in terms of the Chern classes, and then the Segre invariant would be the integral over this virtual fundamental class of the top Chern class of V. Some number, and then there is a conjecture.
Is there a bird on the fundamental class?
Yes, certainly. I mean, it was just invisible. And the conjecture is that if one writes down the generating function, which so there is an explicit change of variables, which identifies the generating functions. So I will not. So this is conjecture with time, based on a similar conjecture. I mean, the generalization of a similar conjecture for Hilbert schemes of points, which was reached by Johnson and then made more explicit by Marian van de Pande. And I will, therefore, this is all I say about the Segre invariants. So whatever I conjecture for the Verlinde numbers will give me a conjecture for this. So we want to find the conjectural formula for these, and so how does it look like?
So can I just ask, what is this KC? That hasn't come up anywhere else. What was the point of writing that by now?
Okay, because I maybe forgot to write something, namely, that's so let be in AC. Sorry, I'm a little bit. So we can define such a determinant band bundle under this condition, otherwise not. It's somehow, this is the condition which makes this thing independent of the choice of the universal sheaf. Otherwise it would not be. So the, okay, and okay, so that's, okay, so let's go on.
So, but then, the Verlinde numbers are only defined for KC.
Yeah.
The Segre numbers are defined for all K-theory classes. But
yeah, but that's okay. I mean, the
change of variables will take care of it.
Yeah, that all takes care of it. And somehow this thing with the KC, this is why we have to make this stupid twist. Okay, so just, I should say as a notation, I write this lambda V, or V AC of rank n. I write this as mu of L tends to E. R for L is equal to the first Chern class of V plus n divided by R, the first Chern class of C. So this is somehow, in a suitable sense, so this, obviously when you twist the universal sheaf by a line bundle, this line bundle would change, but this precisely compensates it. So this is actually, if you take the projection to the, well, anyway, so in this way, the L is independent of the choice of the universal sheaf. So, and now let's first look at the case of Hilbert schemes. So we are interested in some kind of, which is the special case of this. So if you look at the moduli space for any ample class of rank 1, sheaves, let's say 0, check and Chern class, this is just the Hilbert scheme of m points on S, by the sheaf parameterized here is the ideal sheaf. What? Where? Lambda V tensor OX where? OX upper where? DIR, the virtual. Oh, but it's not OX, obviously, it's OMC. That's why you can't do it because it's wrong. Okay. So in that case, we have this picture. We have the universal family inside S times the Hilbert scheme. And with these projections, and we find that universal family and we find that in this case, so we have again the tautological sheaves. So in this case, we don't need to use this lambda v. So if v is in is a gas in a Grothendieck vector bundles on S, we have the corresponding tautological sheaf. So we have dm, which is equal to p plus star p, which is now the vector bundle of the Hilbert scheme. And we actually find that if we take the determinant of this vector bundle, this will be in our notation mu of the first Chern class of the tensor E to the rank of E. Okay, so this is how it comes here. And in this case, this E is actually the first Chern class of the tautological bundle associated to O, which is also usually called AE on the Hilbert scheme. So it's 1/2 the exceptional divisor of the map from the Hilbert scheme from the symmetric power. So in this case, we have a universality statement which says that, so which proved a long time ago.
What is mu?
Okay. So I have this, if you really want, so you have a, basically, you can take, I'm not sure I get the numbers right, but if you take C2 of the universal sheaf in general, in this case, it's just the fundamental class of the universal sheaf, and you take the Salam product with L with some class in the second cohomology, so like L. So that means you multiply this. You multiply this with the pullback of L from the surface. Then this is mu of L. No. So this is what is called mu classes in Donaldson theory. So, so in that case, we have the following universality, namely there exists some universal power series Fn to Gn, Fn, An, Pn, which are some power series in a variable t, which depend only on n. Such that if I take the sum over all m of the holomorphicEuler characteristic on the Hilbert scheme of endpoints of this mu of L tensor e to the n, this is just given by the product of these things. Here the holomorphicEuler characteristic of L, of the line bundle corresponding to L, Fn to the, say, holomorphicEuler characteristic of S divided by 2, An to the L times Ks, and Dn to the S squared. So there are somehow 4 numbers in this business. So you do this, and 2 of
T's are missing on the left. I imagine.
what?
Some T is missing on the left.
Yeah, that is maybe true. The usual one.
And M equals N.
What?
And M equals N.
Okay, yeah, not this, but this, yeah. Okay, so sorry, that seems to be not that. And so that is therefore very true. Okay, so we have this. And in this case, 2 of them are known, so Gn is just equal to 1 minus y. Fn is equal to 1 minus y n divided by 1 minus n squared y. Now I can tell you what y is, because we have with a change of variable that our t is equal to minus y times 1 minus y to the n squared minus 1. Okay, so there is so we have these 4 universal power series. 2 of them are quite simple. Particularly, they're very simple after the change of variables, and that is my answer. So this is, in particular, you have this universality that the answer depends only on these 4 universal power series. And this works for all S, for all surfaces and all line bundles, and all N. Okay, so this is this universality state. Now, we're interested in proving something in the general case. So we want a formula. So if you want the formula, it has to be in certain terms. And so the first step is to have some kind of universality also here. And so this for the modular space of sheaves. And so this is the first thing I want to talk about, but anyway, we're not quite there. So we want to talk about the structure formula for higher rank. So there's one, so we want to find this conjectural formula. And so first we have to find an analog of this universality, but it isn't quite as simple as that. We don't have just these universal power series. We don't depend on anything. There must be some dependence on S, which is already, which is known to be the case for all invariants you want to do for surfaces, namely the Seibert-Witten invariants. So we have to, so the new ingredient are the Seibert-Witten invariants. So if you, so by itself they were defined as differentiable invariants of differentiable form manifolds, and we kind of replaced the Donaldson invariants and somehow destroyed Donaldson theory. But in algebraic geometry they are actually quite simple. So if S is a projective surface, so smooth projective is always smooth. And so I can take for any class A in the second cohomology of Sz, I can associate the Seiberg-Witten invariant of A, which is some integer. And this will be non-zero only for finitely many A. So say if Pg of S is bigger than 0 and P1 of S is equal to 0, which are the conditions we have, these are non-zero only for finitely many classes, which are called the Seiberg-Witten classes. And it's particularly simple in if, for instance, the canonical bundle contains a smooth reducible curve. So if the canonical linear system contains a smooth connected curve, then we find that the Seiberg-Witten invariant of the class 0 in the second cohomology is 1. The Seiberg-Witten invariant of the canonical class is chi of OS, minus 1 for the chi of OS, and all others are 0. And what will be important for us is also so if S hat to S is the blowup in a point with canonical divisor T with the exception divisor so this has quantity P I then it follows that the Seiberg-Witten invariance of the pullback of the class A on the surface is equal to the Seiberg-Witten invariant of A, and it's also equal to the Seiberg-Witten invariant of A plus the exception divisor, and all others are 0. So that means the Seiberg-Witten invariant on the blowup is non-zero if and only if it comes in this way from a Seiberg-Witten invariant on the surface. What?
A is on S. B is
Yeah.
on S.
Yes, that's. Yeah, there's a P upper star.
Yeah.
Okay, so I usually. Okay.
If a canonical, if I'm in this PG equals 1 setting and I only have a singular canonical curve, are the finitely many the pieces of the curve?
So the yeah, there's the so yes. The thing is, the Seiberg-Witten classes are always the subcurves of a canonical curve. So that's also how this comes to pass. So there's then with Martin, so we did a lot of work trying to compute this Verlinde formula using Mochi-Tsuki formula which relates computing of invariance on modular space of sheaves, so modular space to Hilbert schemes of points. And one thing we came up is with a conjectural version of this universality, which I hopefully can show you. If it works.
Can you use this board?
Yes, I can. Okay, so this is not very inspiring, but okay. That doesn't work. That's very sad. Okay, so I want to write down this conjectural structure formula, and so I don't know why it doesn't work. It's very strange. Okay. So we have this n and this r. The n is is the rank of this V, of which we take the determinant line bundle, and R is the rank of the element in the moduli space. And now, if you look so now we have that we have a very similar formula to the case when to the Hilbert scheme case. So we have these two universal power series corresponding to. So let me say it again. So there are now a bigger number of universal power series. So we have one of them. Some of them are these F nu and the G nu, which have the same role as before. They are corresponding to taking the power of the holomorphic Euler characteristic of L and taking the holomorphic Euler characteristic of the surface. And as you see, they are actually the same power series we had before. I don't know where I wrote it.
Behind there.
What? Ah, behind there. So that's okay. That was a very good planning. But just for 1 second, you can see here that we had it. Yeah, I'm very good in and so this was the and so then the claim is that we write down the product of all these power series, of which all of these are currently unknown. These are some power series in T to 1/2, and then the holomorphic Euler characteristic of our line bundle is the coefficient of T to the 1/2, the virtual dimension of the moduli space of this incredibly complicated product. But you see, so what we have here is we have the dependence on the canonical class by its intersection with the canonical of L with the canonical class and Ks squared, and then we have the dependence of on the Seiberg-Witten classes. If we are in rank R, we need R-1 Seiberg-Witten classes. We take their product. There's a sign here depending on the first Chern class of the moduli space, and then we have always the intersection of the Seiberg-Witten classes with our L, and the self-intersection of the Seiberg-Witten classes, and the intersection of two different Seiberg-Witten classes. So we have all the numbers we can make out of the canonical class L and the Seiberg-Witten classes, and we make this universal formula. And the claim is, again, these universal power series, which we don't know for the moment, depend only on R and N, and these two here, which we know explicitly, by definition depend only on R divided by N, so on N divided by R, so in particular also on R and N. Okay, so this is this formula. Oops, and there it goes, but anyway. There's again. Okay, so it stays here maybe for a moment while I now try to see what one can do with it. So we have this structure formula. And so just want to remember a couple of things about it. So we have
Other special cases for which it's proven?
Yeah, it's proven for K3 surfaces. But then it's also kind of trivial. No, I think in general, and the Hilbert scheme case is a special case of it, and in that case it's proven. But that's also fine. Okay. So we just want to remember that the power series that we don't know are the ones that depend on the Seiberg-Witten class of canonical class. So we have these power series A(n), which are to the LKS. We have Bn to the Ks squared. We have AIN to the AIL, BIN to the AI squared, and we have BIJ to the AI times IJ. So these are the unknown ones, and this is, and we, in order to have an actual formula, we need to know all these powers. And so it is convenient for some purposes if we have a subset J in the set of numbers from 1 to R minus 1, we can kind of collect things here. I write AJ to be this AN, so AJN, times the product over all I in J, AIN, and BJN to be BN times the product over all I in J, BIN times the product over all I smaller than J in J, BIJN. And then knowing these is equivalent to knowing all these. Okay? Because I can obviously recover. For instance, we have that AI is equal to A corresponding to I divided by A corresponding to the empty set. Okay. So that's okay, so we, for the moment, are not no further looking at this. So this is the structure formula. And now I want to try to understand these. Why does it do that? Fourth place. Okay. What? Yeah, I don't want to show. I mean, you have now memorized it. There's no need to. I mean, what you have to remember is that we are interested in these universal policies which depend on these powers.
Maybe move that one up.
Okay. So now, how do I want to do this? So the thing that one uses to try to determine them is the blowup formula. Okay. So it's a standard thing. So if I take P from S hat to S, the blowup in a point, then let's say D is the exception divisor. Then it's a standard thing that it's always a very good thing to try to understand if one wants to compute some invariants, to compare them for S and the blowup. Usually a lot of structural information about the invariant is contained in a blowup formula. So blowup formula will contain a lot of structural information. About the invariant. So let's look how is this in our case here. So partly based on the computations with my time, I found some kind of conjectural row formulas which says the following, and maybe we'll not be completely precise, so say C is a class in G0 of S of rank R, and we have N is smaller than R, so these only hold when the rank of the bundle V, that we make the line bundle of the smaller than R, smaller equal for something. And then we have two kinds of blowup formulas. The first one could call identity formulas. Namely, so say if I take for K from 1 to R, if I take the virtual holomorphicEuler characteristic of this moduli space on the blown up surface, and I take the pullback of C as the K-theory class of the, which determines the moduli space. And I take as my line bundle the pullback of L, twist it with some small multiple of the exception divisor. Okay, this will be for k from actually 0 to r. This will be just the same as we had on the surface before moving up. Okay. So this is the first blow formula. So if you don't change the first Chern class and you twist the line bundle with the small power of the exception divisor, then nothing changes. Okay, this is checked numerically up to a certain level, and it also holds in the setting of framed sheaves by work of Nakajima and Yoshioka. And there is, I'm not precisely sure, Kuhn wanted to maybe prove it, but I'm not sure whether he has done it or not. I'm not sure whether he's here. But anyway, and a similar formula holds, there's also a vanishing result. Namely, now we do twist the first Chern class, so that C hat in element in P0 blow up, such that if I take the first Chern class of C hat and multiply it by the exception divisor, this is a small positive number, it's a 1 minus 1, and maybe I don't want to be so precise with the precise statement, so if I take now the virtual holomorphic Euler characteristic of this moduli space, mu of L tensor E to the n, this will be equal to 0 for small negative intersection L times. So I maybe don't specify what it precisely is. So we have, in some cases, we get the same on the blown up surface and on the original surface, and in some cases it vanishes. This has to do whether we twist the first Chern class of the modular space or we don't. Okay.
Do you have any sort of heuristics why such things might be true? It is purely inferred.
Well, I mean, there is some kind of argument, and basically it says something like, more or less, if you push forward the fundamental class of this moduli space, or in K3, it will be the fundamental class. And here, if you push it forward, it pushes forward to 0, something like that. Yeah, I mean, some statement of this kind, if one does it carefully enough. Okay, so now with these blow-up formulas, so the thing is, these are actually, it's not so obvious, but they're very powerful. So you can use them to, you make these, all these power series AI and so on, D, Ej, you make them power series with indeterminate coefficients, you run them through these equations, and recursively, by solving at each step some linear equations, you determine all the coefficients. So this is enough to determine all coefficients of the A and B series.
Is that like a mathematical statement or heuristic? That like, is these actually completely pin them down? Is that like
No, so I mean, I checked it by doing it, so at least for R smaller 6. So I just wrote a program which does it. For I equal to 6, and I determined modulo y to the 100. Okay, so where y is this power series which you have, or whatever, you could say the t to the 100 is the same, which is created by this change of it. So we know this, and so we can look at what we get. And so what we find is very...
R is the rank, and you have as many subsets, and then 2 to the r minus 1 of this card series, or twice that many, or something like that.
Yeah, so if I do it with these j's, I have 2 to the r minus 1. If I do it with the other one, it's a bit less. It's some kind of binomial coefficient, but whatever. But anyway, one can determine them. You know, you just you have to give the computer some time, works on it for whatever, a couple of weeks, and it will give you what. And anyway, and then you can, once you have that, you can play with it. And there's something defined. So for one thing, and so you can observe what you see. And the first thing that you see is that these things satisfy some algebraic equations. So if I take the AJN, BJN, satisfy algebraic equations of, unfortunately, very high degree, as we noticed, of degree 2 to the r minus 1. Namely, the obvious one, the obvious thing is true if I take just the product over all subsets, and I take x minus, say, a, j, n. This is actually a polynomial in x with rational function coefficients. And I can say explicitly what they are. So it is, and the same for b. Okay, so in that sense, so we see that these are always given by algebraic as solutions of algebraic equations, but unfortunately of an incredibly high degree. And obviously these are rational functions. So the degree of the rational function is kind of similar to that, and so it's an enormously big thing. So that's not so nice. But
mean j subset to r minus 1.
Yeah, r minus 1.
Subset.
Yeah, that's also true, but okay. Yeah, I'm terrible with. Okay. So, but there's one thing one can notice. If one, once one has these powers to these polynomials, one can look at them. And there's one thing that one notices, namely, this polynomial for the A series is very nice in some way. Namely, it is almost palindromic. So what we have is, if we write Prn of xy to be this polynomial, to be almost this polynomial, and we have now x minus not precisely this, but 1 minus y to the n plus r minus 1 divided by 2. And then the same thing. Then this is palindromic. So that means we have, if I take x to the 2 to the r minus 1 times Prn of 1 over x, this is equal to Pi of x1. So what does that mean? That means that whenever one solution of this polynomial is this, then it also contains the inverse of this thing as a solution. And so the easiest conclusion from this is, or at least as a good guess, is that if I take if I take 1 to r minus 1 minus a subset I, this is equal to 1 over, the stupid factor, and here we have AI. So this is what this is the easiest explanation for this fact. This is basically this. Okay, and then if one is a little bit more careful, one can, once one suspects this, one can hope that there's an even simpler relation between them, and this is what we actually find. So let me see, as usual, so we have still the same as before, and now, why doesn't it? Huh. So we find that one explanation for this phenomenon here is that if I take AIN, it's actually given by the AIs, where the AIs for which are where the I lies in our set I are in the numerator, and the other ones lie in the denominator. And we check, and it's true for all the coefficients we have. And so this means that we don't need to know what this AN empty set is. We just need to know the A small i's. And then once we know that, we obviously try to find out what the AI is, and so play with it. And then some miracle occurs. Namely, we find that these AI, if I take the rth root of the AI, these are incredibly simple. Namely, they are just the inverse functions of some very simple rational function. So the rth root of AI is just the inverse function of this rational function. Is one branch of the rational function. So it solves this algebraic equation for all I. And then, now as we have been able to express our AIs in terms of these elementary pieces, we can hope that we can do the same with the B's. And this indeed turns out to be the case. Namely, we get this, unfortunately, I don't know why, not so simple formula. So we are again in the situation that there's always the assumption that n is smaller than r. So this is an issue. And we write this thing, and then this ER, so the one of these things, the corresponding to the empty set, is given by this slightly strange rational function in y. So we have the same change of variables as always. And then, so we have our AIs, and we take also the AI to the nu with this stupid root of unity. And then we write down this expression, which is obviously rather complicated, but given how complicated the algebraic equations are that these things fulfill, it's incredibly simple as compared to what it could have been. But anyway, so this is this formula, and you can see it has some nice symmetry. And how nice the symmetry is, you can see if I take any other subset, I, it's obtained from this BR as follows. In BR, we replace the AIN by its inverse and the alpha IN by its inverse whenever I is in I. So with this formula, I've given you the formula for all of them. And so this gives a complete answer when this n is smaller than r. Now I'm a little bit later than I did. Okay. And so now I have to, okay, so this is the formula. And so now how to get to the other case. So, and I think I can only see it very fast. So this is by strange duality. So we cannot use the blowup formula when n is bigger than r. So we have to do something else. We somehow have to exchange n and r. And this we do by strange duality. So note that we can make, if V is in Kc, which was the set of all V in P0 of S, such that chi of V tensor C on S is equal to 0, then we can make our line bundle lambda V in the beta group of MC. But obviously, if V is in KC, this is the same as that C is in KV. And so we get also lambda V, lambda C in MV.
KV.
Yeah. And so Le Potier's strange duality, which is the analog of the strange duality for modular space of vectors on curves, just says that, now you can see some nice landscape, says that in that H0 of MC lambda V will be equal to H0, or will be dual to H0 of MV lambda C. Well, most of the time, so when things are good. And my kind of version of this conjecture says that if you work virtually, they are somehow always good. So the conjecture is that we have that the virtual holomorphic Euler characteristic of MC lambda V will be equal to the virtual holomorphic Euler characteristic of MV lambda C. Say if R is bigger than N is bigger than 0 and C1 of V is sufficiently ample. Okay? And one can make this reasonably precise. So we can use the strange duality to so as we know these as we now have a formula for the AIs when R is bigger than N, we also know the powers. Now we also know the power series when so use this to compute. Basically none. So then the A, I, N, B. So N is now we are in rank R, and the what was N is now R for all I, and for I, 1. Okay, so we can do this. So what does it tell us? So maybe now I don't have so much time, but maybe I can say it in words. We find that now, for instance, this AIR with N replaced by R satisfies the same equation as when we switch N and R with the variable Y replaced by 1 over Y. So we get the same algebraic equations there. And now there is one small issue. So we would want the same formulas as in the so we want to have the same thing, for instance, that all the A series are expressed in terms of the A small I. But this is actually not true. So let me say it. So we put say A, I. So we assume that N is bigger than R is bigger than 0. And we put A, I, N to be just A, I, N. Okay, so this we do for I from 1 to N minus 1. So according to these things, so where these things are now, so the A, the I, and R are now all solutions of this polynomial P, say, N are, like we had before, of 1 over x, 1 over y. So we know that the ones until for corresponding to subsets of 1 to r minus 1 correspond to actually the actual series which we need to use to determine the power series. But the other ones are just the other solutions. And we just use them as if they were also corresponding to some other given class. And with this now, we can actually do the same as before. And then I stop. If I can make it work, okay. So where was I? So we have the same thing here. So we, again, the AN, so these power series which, so the one power series that we need in addition to the AIs is just again given as a product of these AIs in the denominator with the same formula as before. There's only y to the r in the numerator, which wasn't there before. So this means this we only need to know these AIs as before. Then I don't know why this doesn't work. And now we can also again express again these power series AI, which make the building blocks of our universal series. Are again the solutions are basically again the inverse functions of simple rational functions. So the first few ones, which correspond to the actual Segre invariants, are given by the same as before, the same one, and a very similar one for the other ones.
Do you have a psi also in the formula too?
No, it's I have an eta here. It's different root of unity.
It looks like the same above and below.
Yeah, but that's okay here. Because it doesn't cancel because of we have different powers. So it is meant like it is. Okay, and then finally we can also do the same for the B series. The B series can also be again. If you look, the formula looks extremely similar to the case n is bigger than r. We have the same alpha i's, which is again the root of the AI's, and we have basically the same formula. There's only some small difference. We have no, I just finish it. Okay, we replace so what we just do, and again we do the same thing. The BI's are expressed in terms of Bn by making the same change as before, and what we actually have is it's the same formula as when the rank is bigger than the level, so I mean r bigger than n, except we make this exchange. The y is replaced by 1 over I, n is replaced by r, and so on. This is the formula. And then the final statement that this formula is true for Hilbert's use of functions. Okay, so I'm sorry I went over and also went a bit fast at the end. I somehow underestimated how much time it takes to write on the blackboard. Okay, thank you very much.
Questions? Comments?
Nobody?
You've blown everybody away.
Yes.
So just do you envision some like way to prove these conjectures or like?
Well, so I mean, if one, so there's two things up. So the first thing, this structure conjecture, and basically Joyce has this, I mean, as you also know, has this program to basically prove a version of this structure conjecture by some kind of very big machine which proves a just much more general version of it. And if he proves precisely, and I mean, the hope is that he proves it in a generality and in a precision which actually will give all this, and this is reasonably likely, but you know, as you know, he has written like 1,000 pages about it, and a few more will have to be written, and then most likely this conjecture will be true. The blowup formula should also be quite provable. As I said, Kuhn wanted to prove it at some point, but it might be he found more interesting things to do, but you know, at any rate, it is quite doable. And at least to some big part, of this might follow by careful analysis by just proving these two conjectures. So instead of just doing computer calculations, you actually could try to argue with these conjectures, and it might be enough to actually prove the formula when n is smaller than r. The strange duality is a completely different story, and that I don't know.
Your universal sheaf always exists?
What?
You always assume that a universal sheaf exists on the
No, I think I mentioned, I don't really need that it exists. So for simplicity, I wrote that the universal sheaf exists, but these line bundles are, can also just be defined in terms of some descent from the quad scheme. I mean, there's no issue. This condition that B is in KC is enough to make sure it will always descend, whether the universal sheaf exists or not.
over the full moduli singularity.
Yeah, okay, so I have to be a little bit more careful. So if we have strictly semi-stable, then one has to make this KC a little bit smaller. There's some somewhat stronger condition, so not just that it's orthogonal, but something a little bit more, but then it will still be true. So with a small correction, it will always work. But if stable is equal to semi-stable, then there's no issue.
Do you have any geometries or classes where you can actually manhandle this, like elliptic surfaces or something?
Well, I'm not sure. I mean, it could be that elliptic surfaces would be easier. Obviously, the case of Hilbert's of K3 surfaces is kind of easy. You can reduce it direct to the Hilbert scheme of points, and in the case of Hilbert scheme of points, it's proven. So then it follows. But somehow most of the issues that are in the formula are then not there. So it's kind of not proof of anything so relevant. For elliptic surfaces, there could be some arguments, but I haven't seriously thought about it. I mean, you could have some. I mean, it is possible that you may use some Potier story or whatever, but I mean, I have not seriously thought about it. And I mean, yeah, okay.
To reduce to the right point.
Yeah, something like that.
You have a question?